Welcome to today's webinar. The topic today is membrane structures with wind loads from CFD wind simulation. My name is Andreas Hörold. I am responsible for marketing and public relations, for instance, the Dlubal website, press releases, webinars, etc. I will moderate this webinar. My colleague Andreas Niemeyer is going to do the live presentation in RFEM and RWIND simulation. Among other things, he is responsible for the add-on module RF form finding, the standalone program RWIND simulation, customer support, etc. Okay. On the right side of your screen, you can see the control panel, and you can open it and ask an individual question. I will answer the incoming questions. If you don't get an answer during the webinar because there are too many, you will get an email after the webinar. The other maybe better way is to watch the entire webinar and then email your question to info@dlubal.com. You see it here below on the right side. Now, Andreas Niemeyer will say something about the content of the webinar, and then he goes directly in the programs. I will hand over the screen to Andreas. Just a moment. Andreas,
okay,
your turn.
Okay, thank you, Andreas. I'll start immediately with the webinar, Wind Load Generation for Integral Membrane Structures. In fact, quite a complex title. It's especially the last expression, integral membrane structures. With these words, I only want to mention that I show today everything on an integral model means I simulate membrane and supporting construction at once. This whole model or this whole presentation have two main focuses. The first is the modeling of the membrane structure itself, and the second is the generation of wind loads for this type of model. I show you this in a workflow. This means modeling, loading of basis loads, wind load generation, combination of loads, and afterwards we take a look on the design of a few members. In the second advanced part, I want to rethink this model, or at least the wind load calculation by means of the consideration of bodies which influence the wind flow around model. But to this topic I will come later. As you can see in my picture here in this slide, I have here a membrane construction based on two frames. The mid frame is a frame with a curved beam, top beam, and the in front beam frameworks is consists from two columns and a horizontal beam. In back, we span down the construction with a pendulum column, and these three elements are leads me to the next step, what I want to model now. Therefore, I jump into the program, RFEM, open a new sheet. Let's give the name VER, for example, and use a 3D environment with a z-axis upward. And then we confirm this setting and get here an empty environment where we can create now this model. At first, I want to start with these frameworks with a curved top beam. And here we say that these two columns will placed here in origin and 20 meters beside. We know from these columns that we have that they have a length of 7.5 meters, and with this information we go into the member function and go into library and select here the column cross section. It's a hollow section, circular hollow section with a diameter of 270 millimeters, with a thickness of 10. This we assign to a standard steel, I would say, S355. And after confirmation, we can place the member in the space, but we know that the member have a length of 7.5. Oh, not the wrong box here. No. Now, 7.5 meters, and this column will be placed perpendicular to this grid plane. So I can place it here on origin and 20 meters beside. Now we can start modeling the curved beam on the top. For this, we have to, let's say, specify the sag. Here I use a function to create a node in between. And this in between node, we move now 2.5 meters upwards and get so the geometric of this arc in between these two columns. Here we use an arc function and pick only these 3 nodes and get finally this curved geometric. At the moment it's only a line, but we can assign to this line via the properties a cross section. Here I say the member is available and we assign the given cross section the same like for the columns. And so now it looks that the frame is already done, but we have some overstands here on the right and left side. The overstand is running in the same curvature like the main beam and have a length of 1.5 meter. So it sounds easy to model this, but it isn't. And especially the demand that it's running in the same curvature. For this, to get here this overstand, I activate at first the display of center nodes of this arc. I go for this into this display navigator, go to lines and say here, please show me center points. This leads to this small cross here on bottom, and this cross represents the center of this arc here. And with this information here, I can rotate this node around this node and produce here by rotation a new curved member in the same curvature like the main beam. So I select this node, go into rotation function, say, okay, please copy it one time, rotate around y-axis, and the rotation point is this node. Now the question appears, which angle I have to use to get a length of 1.5 meters. And the question is, I don't know right now. So I use a big increment, for example, here 30 degrees, and say, finally, please create me from this origin node between the copied node, a new member with the cross section what already is given. And after confirmation, we should get here a pretty long overstand. Of course, it's longer than expected, but we pick it and say, please divide it and divide it at start with 1.5 meter. So then we can delete the rest and our expected overstand remains. Now we take this overstand because we need it also on left side and activate the mirroring function and mirror this overstand from right side by copying it with the plane CY, which is going through this node in the middle and on the other side. But before we deactivates a special function to produce new members. And so we get also on the left side this overstand. Now it seems really that this framework is finished and we can go to the next. Of course, we can do this, but I want to secure for further result interpretation that, let's say, the bending moment My is an in-plane bending moment and the bending moment MC, for example, is an out-of-plane bending moment. And to realize this or to fix this, we have to check member axis systems. And for this, I activate this member axis systems here in Display Navigator and use this member axis systems. And if you take a closer look on this, you see here is y-axis perpendicular to member plane, here z-axis. So we have a mess, let's say, here. And this leads to the situation that I have to orientate it according my expectation. And for this, I create in the middle a node, for example, this node here. Select all member properties, right click, member edit, and assign it to the right, or let's say not assign, then to orientate it to a special node. And this special node is here, this node number 13, what we just created. And here we say, please orientate all these axes, axis what coming out of monitor here, and z-axis is here the weak axis according this node. And after confirmation of this, you see the y-axis is perpendicular to plane and z-axis is inside. So now everything is fine and we can go ahead. And we go ahead with the second frame in front of the construction. We know that the in front beam frameworks is 7.5 meters away. So we take these columns and copy it, move copy, 7.5 meters in front without elevation change, and we copy it. So now we get here two columns and we modify it that it represents the in front framework. For this, I take the coordinates of this top points and we change it to the real height of these columns. In this case, it's 8 meters. Okay. And again, we know that this frame in front is a little bit inclined out of the construction. So in this side here in right direction, therefore we select this node and move it in this direction without copy in minus y direction. In this case, it's 2.8 meters, 2,800 millimeters in this case. And now you see the inclination is done. The only job what we have to, or to finalize it, we have to connect these two top points. So I take a member function and place here a member between these 2 points. To secure here also a good orientation of coordinate systems, I do the same action like for the previous frameworks. I produce here a node in the middle, select all beams and assign it to this or orientate it to this node. So help node, select this node and XZ plane. So now this is also done and we can go to the next support element. And this next support element is the pendulum column in the back. And the pendulum column in the back is 5 meters away from this node. So we take this node and copy it 5,000 millimeter in left direction. So 5,000, copy, and okay, and we get here this node. Now we take, for example, a column of this mid frame, place it here on this node what we prepared, and change again the top point to the real expected coordinate. In this case we have 7 meters, and we have again here an inclination in left direction, so I activate here the move copy function with 0 copies and move this node 2 meters into the back direction. So now this leads to the situation that all main or primary construction elements are modeled. This is a framework of 1, framework 2. Here we have a pendulum column, and to avoid final, let's say, numerical issues, what means rotation of beams around her axis, I change it here to a truss member. So, but what we see when we take a look on these elements, considering it or seeing it without supports, these elements will be fall down to bottom because they are not fixed in horizontal direction. And this is our next topic or job to do. We have to fix this element that they are remain on its place. The same issue is on site when the workers create this construction elements. These elements should be built up and should fixed with any cables that they hold itself on site. So we model now here some primary cable construction which is only here to fix these elements. What means we lead or we take a cable from bottom, span it to this top point, to this frame top point, to this frame top point, and down to bottom, the same on right side. To do this, I need some fixation points on bottom, what we have to create now. This means here we take this node from top, copy it with 1 copy, 3 meters in positive Y direction, and that it appears on bottom, we move it down for 7 meters, -7 meters. Okay, so this is the first fixation point, and the second fixation point is here in front. So we take this node and copy it 3 meters in negative Y direction. So this means I have only to add here minus, and in X direction we move it -2 meters, and here that it appears on bottom, we move it down 8 meters. So now we created these 2 foundation points, let's say, and we can create the cable in between. For this, I go to the member function, change here the member type to cable. Of course, we cannot make a cable from this big cross section, so we go to library and go to solid sections here, and use here a PE cable with diameter 20 in this case, or description 20, and assign it to corresponding materials that we have a right stiffness for this cable. Now we take this node, what we prepared, connect it to this top point of pendulum column, go here to the next framework, to the in front framework, and down to the bottom. As you see, this cable cross section is so thin that we don't see it, and for this I changed to wireframe model. What helps a little bit in this case, I defined the colors like this, that we see beam elements in black, truss elements in dark blue, and these cable elements in green. Now we take maybe a look from top view, and you see this cable is also needed on right side. So we take it and mirror it on the other side, and okay. So now this primary structure is done. The only thing what is missing is the support on the bottom points of construction. So we take here a nodal support, produce here a new setting, and take here really a native hinged support, what means X, Y, Z are fixed and the other degrees of freedom are open. And for this, I select these two nodes, left and right side. So now all points are supported, and this basic primary structure should be stable and should be calculatable. And this is what I recommend now to try. So here I recommend to create the self-weight locus, for example, with self-weight factor in -c, and we start a calculation on it to see if the program finds an equilibrium, and if it finds something, it's a sign for us that we did everything right. Of course, the deflections, like we see it here with these big sags, are not what we want to see, but this is not the case now. Here is we only want to check if we did all inputs, if everything is defined, if supports are done, and the reaction is in our further task described, but not now. But this result leads us to the situation that we have to model now the secondary model, what means the membrane with its boundary condition. And membrane, like you saw in initial picture, I deactivate now results, is connected to this straight beam in front, is spanned over this curved beam and spanned down to the back to bottom. So here we have all support construction elements, but what we haven't is the boundary conditions for the right and left side. So when we take a top view, we have to fix the membrane here around with any supporting construction elements. In my case here, it's cables, but we have to model these cables, and I plan here to define here a cable. So here in this segment, the same here in this segment, and span it down to bottom. So we create this construction elements by copying at first the basis nodes. So we start here at first from this bottom node of the mid frame, copy it here with one copy. In X direction we use -2 meters. This is fine. In Y direction we use -4.5 meters, and the altitude is in this case 2,500 millimeters. So this is let's say definition node, and to this node we connect the cables. I draw, for better imagination, I draw now this cable, or at least only the line, and this, now you see, okay, this is the geometric, and this node we span down now to bottom, and here we take this node, copy it, and move it here in X direction with -884 millimeters. In Y direction we have to do nothing, and in Z direction we go down to bottom here like this. And so I can combine these 2 points with a line. To finish it now, the boundaries, we go now in the back segment and do the same. Here we start again from the bottom node, from this last column here, go here to move copy, and take here in X direction minus 7433 millimeters. In Y direction we do nothing, and in elevation parameter we use 2.5 meters again and get this node here. We connect this node here also with the top points, so we can see that the membrane is placed here in between these lines. So that we can fix this point here, we need also such a span down cable or geometric. So we take this node here and copy it here minus 1 meter in X direction and 1 meter in Y direction and go down to bottom. So this is now the end of this pretty complex geometric definition, because now the most critical geometrics are given and we can start modeling. We assign to this, let's say, 3 line elements a cable cross section. So we go here to line properties, go to the member top and select here a cable element with the corresponding cross section, and let's expect that they get a green color. And now we can mirror it on the right side. So we select it here and mirror it with the given mirror plane in the middle. Now you see this represents now the boundaries for the membrane. Membrane will connect it to the straight beam here and to the cables around, and could so give its forces to the basis construction. The only thing what we have to do now regarding cables, we have to apply the remaining supports, what means these span cables should be fixed on bottom. So cables are done now. What leads us to the next task, to define the membrane in between. But to define a membrane, we have to give the properties of the membrane. For this, I change to the material table. Write in the third line, for example, the name membrane. With return, you see all values are 0. What is not so nice, the program don't know the word membrane, but we can give the properties of a membrane in its sub settings, because we apply here a membrane with a explicit warp and weft direction, means different stiffnesses in warp and weft direction. So I select here orthotropic elastic 2D material model, what gives us the option to give different Young's modulus in X and Y direction, what means warp and weft. As you see here, we have a unit force per surface, what is typical for a Young's modulus. But if you work in field of membranes, you know names like force per line. What contains these values contains the thickness of membrane directly inside the value. For this we haven't, but we have to modify or to give a equivalent force per surface value. So we relate it to a specific thickness, for example 1 millimeter, what leads to 3 additional zeros in value when I work with a meter unit. So we know we have a unit of 1000 kilonewton per meter. I write 1000, then I give in 3 additional zeros for the thickness, and now I realize, oh, I have here a centimeter unit, so I write here the unit what I expect, kilonewton per square meter. And after changing the cell, you see the program is changing the value according the according the unit setting what is given here. In the wave direction we have 800, so 80. In the shear stiffness is perpendicular to plane. We have for membrane 0. Because 0 is not accepted from the program, I write the almost 0 value, 0.1 in this case. It's not used for membranes. And for shear stiffness in plane, this is used. We give the value, for example, 3. And again, because there could appear Poisson ratio effect, we type in, for example, here 0.2, which should, or let's say this value should represent our demo membrane material. And you see you have an option to define every type of, or every stiffness relation, whatever in this program. With confirmation, 3 values remains, the specific weight. So if we say 1 square meter should have a weight of 1 kilogram, I write here 10 kilonewton per cubic meter. And thermal expansion we can define, but I don't, because I don't define any temperature load, so this value is uninteresting. And the safety we set to 1. Now we are ready. But to reach, let's say, a different graphical appearance of membrane to our given steel members, I change this blue color to any other color, for example, this fair green. And so we have also a good appearance of membrane to steel, or let's say a good difference in between. Okay, so now our material is given and we can start hanging in the membrane in construction. I do this 2 stages. This means I define 1 membrane in the first part and 1 membrane in the second, and use for this the quadrangular surface type, what allows me to define a non-plane surface. I use here the membrane material and define in stiffness type membrane orthotropic, and in settings it's possible to change the thickness to the, let's say, related one, in this case 1 millimeter. And now I can pick the boundary lines like a circle, and after picking the last line, you see the program accepts the membrane input and draw a dashed line around. This is a symbol that inside this line circle or member circle is a surface, in this case a membrane defined. We do the same for the back. And now also here the dashed line is displayed, and with activating the shaded view, you see we have here some surface definition inside. So now the model looks like finished, but if we take a closer look to these membranes, you see there are edges. It's not curved. It's not PXA curved. It's a surface, but is it really what we expect? When we are working with membranes, we expect such nice homogene biaxial curved surfaces, and these shapes we only get when we calculate it. So at the moment we define only a surface inside some boundary lines, not more. There is not given any more information. When we expect that the program creates such nice homogeneous shapes, we have to force the program to calculate this shape by any definitions, for example pretensions, and this process is named form finding. So the program can calculate or can evaluate the place of mesh nodes according some definitions, according some tension definitions in membrane, according some force or deflection definitions in cables, and gives us a shape which is under tension for further calculation of some basic load cases like snow load case. To get this, let's say, nice shape, we have to give definitions, boundary definitions, and this we have to give for cables and for membranes. And to get these options, we have to activate it, and this could be activated here in general data in this tab options, and here is the option form finding, what opens this process and defines in front of all other load cases a calculation or a task form finding to find at first, according to the given definition and given geometric, a shape. And this process is always done before everything else, that everything else bases on this nice shape. So now we define these boundary definitions. At first, I would say for the cables, it's helpful when we do it from top view. So you see, this was our basic primary support construction. What was only here to support the frames without membranes. So I define for these cables. So here, the cable in between frame mid, in the middle, and in front. I define here in the settings of this cable here a small force, nothing big. It's only here to support this frame. So we define, for example, here 1 kilonewton. The other connected cables, like this here, this and this last one here, get its force from this 1 kilonewton and should react. And here the predefinition is to have, after the form finding task, the same length like now. So this I can define here with target cable relative length, and this value I define to 100%. So now we have defined this, let's say, primary support construction, and we can go now to the secondary construction, what supports the membrane itself. Here we have a cable circle for the membrane, and here we can allow to define a sag which is running inside the membrane. And I would say we take here, for example, a sag relative to the length of the current length of the line with 10%. So now it seems we are finished, but we have 4 cables open, these span cables, what gives stability in construction itself. And for these 4 cables, we define now a force, for example, 30 kilonewtons. Now, the cables are defined. The setting could be displayed if you activate form finding and loads. Now you see all settings what we defined. And for the membranes, we do the same. Here we define at first the isotropic condition, or at least we check it that they have defined it. We select both surfaces, going to properties. Here in property and top form finding, and you see for these membranes this pre-stress 1 kilonewton in X and Y, or WOP and WEFT is defined. So everything is fine, and we gave the program everything to find a nice place of mesh nodes according to conditions and surrounding construction. For this, we run now this process and watch what comes out. I hope we get a nice shape, what fulfill all demands. At least now when we see this graphics, it looks now curved, biaxial curved, much more better than before. We can display the C coordinate by these contour lines. So far everything looks good. Of course we get also to this shape the forces in the remaining elements. The only thing what I would improve or change to show you more options is that we need here a bigger curvature. And that we get here a curvature in both directions, and for this I increase the pre-stress in this direction, and the stress in this direction we let like it is. For this we have to define the coordinate the coordinate system directions of membranes. So I go here, select both membranes. Oh, now I selected surface, edit, and go here to axis and change axis direction, y-axis. What is the wave direction should run parallel to this line. Okay. Now the program want to delete these results because we changed the basics, and after this change we are able to define different forces in X and in Y direction. So if we open again the form finding tab, you will see Y axis is now open, and we can change it, for example, to 2 kilonewton per meter. Okay, now we can do a second run, and hopefully we get a bigger curvature in this in front membrane part. And if we take a look in X direction, you see, okay, this action was okay. If we take a look in membrane forces in X direction, we are near 1, and in Y direction now we are near 2. And this is now the model with memorized force condition. What we can use now for the further subsequent structural analysis. And this leads us now to the next step, to apply a snow load case. Besides the given surveyed load case, we apply now a snow load case. The action category is defined automatically according to the word snow. And for this, we go into the surface load and go here to projected load in Z direction and apply a snow load. Because this model is rebuilt in winter, snow load is not the most important load for this model, but of course we want to consider a small fracture of it, so I apply here 30 kilogram per square meter with minus 0.3 kilonewton per square meter. And for this I select both surfaces, and you see when we watch in X direction that this load is applied per projected, and when we take a top view, then you see that the load is applied on surface. With calculation of this load case, we see that the program find a convergence. We see, of course, here a colored picture. What means this is now forces in membranes. Forces we can deactivate. What is for snow load case is always interesting. If there appear some water bags and so on, here you can change to deflection. These deflections are based on the form found shape. Of course, this looks not so nice, but you have to display it in, let's say, deformation factor 1. And if you need some elevation lines, you can activate it here in this hidden function, show level curves, and you can change it to this what you want, and can visualize if you have some, let's say, almost straight parts. So now, after defined definition of this snow load case, we can go to wind loading. Of course, we can write now here wind loads in x direction, in minus x not needed because it's symmetric, in y direction and minus y direction. But the question appears, how this wind load looks like, because this type of model is not according the loading schemes of given standards. So there is always a struggle. You always struggle how big or which scheme should be used. And this was our challenge to develop a new program called RWIND simulation. And this RWIND simulation is in fact a numerical wind tunnel where we can place any type of model and can load it with any wind in any wind flow and get the reaction, let's say the surface pressure from it. And these surface pressures we can use for further calculation in RFEM and RSTOP. To do this, you have to go to calculate, and you see here we placed an interface to this standalone program, RWIND simulation, and this interface prepares the inputs for this program. At least it takes this model what is given in background, but also the information about the wind flow for which it should be considered. And here we have to define, of course, the wind directions. The wind directions are defined in this first block. Yeah, we can say every 10 degrees increment we want to check it, but imagine this results in a lot of load cases. So in our case, I would say this quarter simulation is okay, but and also we can reduce this with knowing that x is 0 degree, then 0 degree, 90 degree, 180 is not needed because the structure is symmetric, and 270 degrees. So these three load cases are interesting for this type of model. And here in the second part we have to define the magnitude of the wind. Yeah, we have to say that strong wind, not so strong wind. For this, we offer here, let's say, a code box. You can select between Euronorm, American standard, and Canadian standard. In my presentation today, I use maybe Euronorm standard according German annex, and I assume a wind zone 1 with a Terra category 2. And here you see these settings results in this final wind speed diagram. What is the input for the numerical wind tunnel? This diagram represents the wind at this site, plus the terrain information, plus any wind gust effect. And this wind gust effect is already in this wind diagram. But because I assume now that this gusts near model will be induced from the model geometric itself, I say I define in the beginning of the wind tunnel a mean velocity and define near model. The program should react with a specific turbulence model, some gust effects. And here I assume a turbulence intensity of 10%. In the next, after changing this value, you see I changed my top. What leads me to more settings, what you can define here. For example, these flow parameters itself, the convergence parameters, the meshing parameters, and also in which way you want to get back the loads for members, for example, as diagram, as uniform diagram, or as trapezial diagram. but this is only some subsettings what are moved to this RWIND simulation. And finally, this all ends in this mid-top load cases, our 3 load cases, what we already defined in begin for in wind directions for 0, 90, and 270 degrees. And this wind load cases contains now all this information plus model for this numerical wind tunnel test. Now we can finish all this by using this function calculate all in background. This is in fact a pretty boring story now because you don't see something. This process will take 18 minutes, what means 6 minutes per load case. And I don't want to suffer you to watch this progress bar the next 18 minutes. So I prepared a file for it, which already calculated results. So I close this file here and open a prepared file T1. What is the same model with results? I go immediately here in this menu, in this interface menu back. Here we see in the load case tab now that behind these 3 load cases is a check calculated. What is good, but it's still intransparent. You don't see what is behind. So let's take a look, especially what is behind. So we set our cursor maybe on wind 0 degree, what means wind from left to right, and open it in this RWIND simulation program. You see the separate program is started. You see a color picture, it's the model, but maybe to start from begin, we have here a 2-stage graphics. One is only for the model. Here you see the wind tunnel. It defines a space in a rectangular box in space. The red frame is the inlet window. Here we define this wind speed diagram, what we defined in the interface program, plus turbulence settings. Here on the right side is the outlet window. Here on bottom you see the meshing, or not the directly meshing, but a symbol of meshing. That the program have a, let's say, a global mesh density, what is refined near model to get real effects here. And of course, inside this box of wind tunnel, we have our model with curved membrane, members, and so on. What means it will be represented rigid in this calculation. And after calculation, after the 6 minutes, maybe only to know this, the 6 minutes are measured on a standard PC, an i7 6500U, not a machine from hell, in fact, but it's quite fast, I think, compared to this computer. And you get here results on model and also around. This means around the pressure field around. You see here it's a solid result. It's displayed in these slicing planes. This is the pressure around the model. You can display it in the full wind tunnel, and you can display it only in this reduced domain around model. I think this makes more sense to see only the relevant result. These pressure slices could be moved, and you see the difference at any place. You get also a velocity field around. And if we speak from velocity, we get also velocity vectors, what means, or what shows us the direction of wind around the direction of wind in compared to the model or around the model. And if we have this direction of wind and the magnitude of wind, we can evaluate also streamlines. And what is typical for this type of calculations, of this CFD calculation, And you see now here these streamlines, also animated, what gives you impressive pictures or videos, leads finally to the pressure on the model, what could be used for the subsequent calculation. You see here, for wind pressure side, we have a positive value, and in the back we have negative suction values. And of course, and this is a typical question, on the lower side we have, we have also different values than on top. And the interface gives you the resulting force of both sides for further calculation. And this is finally, when we go back to RFEM, here we get now after calculations is 3 load cases. And here you see the deflection, how the model reacts with this type of loads. Here on pressure side, the membrane going downwards, here on suction side it going upwards, with corresponding forces in membrane and on members. Yeah, and if you want to check which forces are given from RWIND, you can use this result load distribution. It's hidden here on the bottom of a result navigator, and here you can take a look on wind load using a wind simulation, which graphics or result plot gives you this resulting wind forces from top and bottom surface to RFEM. So after all these tasks, what we did, we received now a load case list with surf weights, snow, wind, which we can use now for further calculation. And the further calculation is now the the combination of load case. So I open the combination machine, or I activate it in the generate data dialog. Here you can define according which standard the program should combine the loads. I use Eurocode with German annex, for example, and say, please combine it automatically and create load combinations. And after doing this, the program changes something in its internal dialogues, but we can watch this by opening the dialog edit load cases and combinations. Here you see the load case list. Here you see resulting actions from it, what means permanent actions, snow load actions, wind load actions. He defined it alternatively, so they don't work at the same time with combination expressions. And here, let's say for this demonstration, we remove these green ones, what stands for SLS checks, and consider now only ultimate limit state combination expressions, what basis on this formula, typical formula, considering these gamma values, and are created according, or let's say with the calculation setting large deformation analysis on deformed shape, because cable and membranes. And this, considering all this data, we get action combinations. Here you see gamma 1.35 increased permanent loads with snow loads with leading factor, permanent snow and wind. Here snow as leading. What I would say is not so interesting, because this model is rebuilt in winter, so we can deactivate this one. Here we have permanent and wind with leading, and if we have two variables, here is wind as leading. So, and all these rules what we have here ends finally in 8 load combinations, where the program combines everything with this gamma factor. So here we have pure surf weight with snow, surf weight with wind in different directions, surf weight with snow and wind in different directions, but with wind leading. And all these combinations will be summed up in this result combination 1 as quasi-permanent situations. And now we are coming to the next step, let's say to the design step. For the design step, we need forces, and these forces are done or prepared in this result combination 1, what leads to a when I calculate this to a separate calculation of 8 different load combinations, what I just showed you. This I just run, and you see that the program converges here. It converges because the element cables and membrane reacts nonlinear. They can't overtake compressions. And you see also that this curve going up like a stairway. This means we bring up the load in increments. Here you see 5 increments, and you can compare this like we bring up the loads with a watering can on the model slowly, that the model can react and can give results, because we know also if you work with such nonlinear acting models, they could react also numerically unstable, and then this means you get no results for specific load situations, and it is really helpful to apply these loads in these increments. So now it ends and we get results. We get no, what is better, we get no message. So he was able to calculate all results. And for example, if you take a look on bending moments of this envelope, you see here all these 8 combinations leads to, in this case here, to this smallest bending moment and biggest moment of this frame, and of course also forces in membranes. Yeah, when we activate this. Oh. Okay. Okay. So then we remain in these deflections, and yeah, take a look on these explicit results, and I hope now we can display it. Yes, we can display it. You see here, this is maybe combination permanent weight with snow load, or here is permanent weight with wind load, and here, for example, wind load in X direction. And this gives us these forces, bending moments, and I hope also now membrane forces, yes. And all these forces, what we get now from 1 to 8, from combination 1 to 8, we can use in the design module for design of members. But before we go into such modules, we need some stability concept. This means we know that the membrane gives some tension on members, and this leads also to, in specific cases, to compression, and you have to know how you want to design this type of model against this compressions, or how to consider buckling in these models. And for when speaking about buckling and compression in models, it's always helpful to know how critical the state is. And for this, I recommend to use, for example, the stability module, what calculates for you the buckling value or eigenvalue with a corresponding buckling shape. And for example, we can calculate here 10 shapes according the most critical loading. In this case, maybe vertical loading, surface weight plus snow. It's low case 1 and 2. And with this info, you can decide what to do. And it's also quite interesting that you can combine the stability module with this integral model where we created wind loads from a numerical wind tunnel test. You see, it's quite mighty, because RFEM is so programmed that you can combine everything from any source and use it together. And now we get, within a few clicks, the information that for this load condition, the model will buckle if you increase the load with factor of 16. what is in fact a quite good information. This is the result that maybe if you calculate here, you get a magnification factor. Only an assumption what says when we calculate this model according second order, the results will be increased with here 6.5%. What is below the demand of standard, because the standard says generally if the second order effect, P delta effect increases the result more than 10%, we have to consider it. So therefore I say it's a good information. So we below this limit, but we know also we already calculated geometrical nonlinear because membranes and cables. The question appears now only regarding stability design. We know that we are not on critical limit, and we know we already calculated geometrical nonlinear. The only thing what we don't did explicitly, we don't define some imperfections on it. But we can say that the wind load, what we already defined on it, is an imperfection. So for stability design, we can assume in this case, or maybe we can try to check what happens when we assume that these wind loads, what we applied, represents the imperfections that we get from all this analysis what we already did, geometrical nonlinear internal forces for design with a stability effect, with a P delta effect, assuming some imperfections what coming from wind loads. And with this statement, we can say we can design the members according cross-section proof plus stability checks, but not with real buckling lengths, and this buckling length is member length, and this is quite easy. So now changing to the buckling shape to see what is going on here. You see if I increase here the loading with factor 16, this in front beam will buckle with factor 25. You see the member will buckle here in this direction, but all this information is now obsolete because we see it's bigger than factor 10, so we neglect it, but assume for design that we have forces based on wind load imperfections according geometrical nonlinear calculation, and with this information we can open the Eurocode 3 design, say please make us a design for all members, for example here, members according beam and truss type. We select it here and we assign here all combinations 1 to 8 and check it with material what we defined already as 355, cross sections already defined, and intermediate lateral restraints we haven't. Yeah, we can't define. We have a membrane, but this could not be considered like this. So we calculated without, and in this top effective length, as mentioned, when assuming the wind loads as global imperfections, we can say please do the buckling checks with buckling length is member length. This means this factor 1 is okay here. So we start calculation and get a final utilization over all combinations. You see we have the biggest utilization is 0.6, so everything is fine. Maybe as overview what is done now here. Let's move to member design table, and you see the program did for all members the cross-section checks for compression, shear forces, resulting shear force, bending shear, axial force, and also stability checks was done for flexural buckling about Y, about Z-axis, and the interaction together. So this is pretty mighty, yeah. With a few clicks, you get a result, and with changing to graphics, you can display also the utilization of the member length with a diagram. What leads you to the situation that you can start now documenting your model, how it is calculated, and what is your potential or your limit to 1. to not limit to one, but what is the limit of the model. And I said all cross sections are okay for the creation of model itself. So now we are at end of the first part of presentation, and I want to invent a rethinking of this things what we did, especially regarding wind load creation, because when you look at the model again, more detailed, and maybe you watch in my direction, you see that the wind flow can go through the model because there is nothing, maybe a few people, but imagine the event manager decides that the people get something to sit and can watch to the tribune on the right side. But if he decides that the people below these roofs get here something to sit, the sitting construction, the wind cannot run through the model and have some different interaction on membrane or members like we considered now. And this means we have to find different forces for these membranes. And I want to show how our program supports you in this case. And so imagine we have here some stairway where the people can sit. We have to place such bodies in our wind calculation. And to do this, we need these bodies as in any format. And here RFEM is helping you. So we can open a new sheet and can model this construction or this additional bodies in a separate RFEM file. So we open here a new sheet and get here empty environment and start modeling these additional bodies for wind simulation. So I know this seating construction have an available place of 20 by 10.3 meters with an elevation or with a height of 7.5 meters. So we can use this space. And therefore we draw here the depth of this construction is 10 meters. The height in the back is 5 meters, so we write here 5 meters in the back. In front we have 500 millimeters, and the depth of the seating steps is 1 meter. 1 meter in plane. And this type of steps we have more times in globally we have 10, but we have to copy it 9 times upwards with the copying vector from here to here. And this is now the cross section of this construction where the people can sit on. And here I simply define a surface. It's independent if it's from concrete, from steel, which thickness. It's only to define the body itself. So I take this property and define here this surface and define additional also the balustrade. I just forgot it, but we have also balustrade what influencing the wind. So we know the balustrade have a height of 1 meter, so we take this 2 steps high. Combine it with a line, use this node here on the buckle of balustrade, copy this line on bottom here, and combine all 3 points. Oh, I'm too quick. Combine these nodes here, and here this arrow we can solve by moving this node, and define here also a surface for this balustrade. Now, and now we can take this cross section and copy it or extrude it as casing. You see, now we can give this surface a solid. So we have a space of 20 meters, so we use 19 meters, return, and can close this casing by copying this covering on the another side. Now we close this body or this geometric by producing this handrail on top and feeding here a balustrade surface again by picking all 4 lines around. And now we created with a few clicks, really a few clicks, a body for this wind simulation. And to bring in this body in this wind program, we export it here with the export function in a RWIND simulation file, maybe URR, save. And now we can close it, go back to our initial file and go into the interface and go, for example, in Wind 270, for example, so perpendicular to these frameworks, and open it in our Wind. You see, this is the current solution without any body inside this tribune, or not tribunes and grandstand. And now we feed our just produced model. We go here to right side, right click, import model from file, go here and select this URR and confirm it. So program wants to delete results, so this is needed, of course, and the computer placed it without knowing it how it should be placed, but it's okay so far. So now we reset it to any origin. So this means I go to this model and say, please place it on origin, and rotation should be holded because this decides for wind speed direction or wind direction. The same we're doing for this seating stairway 0, 0, -90. And you see, okay, now the orientation is right, but still wrong. So we move it in X, in Y direction with -0.5. Okay, so the distance is okay. And here in this direction, we move it 10 meters in left direction. So this means -10. And the seating stairway have now a good placement. And we can run wind analysis again, and to see what happens when the wind cannot blow without any resistance through this roof. This follows now to wait 6 minutes again. Therefore, I prepared a file which contains these results. What is the same, but with results where you can see immediately the reaction. So you see now here the reaction. Maybe let's take first a look on surface pressure. You see the stairway, this additional body gets also some pressures, and it has some effect also on the inner side of membrane. And if we take a look on these streamlines itself, these streamlines maybe in the middle of this grandstand. For this, we can modify this grid. I'm looking here in X direction to place it on right direction. So here, take it like this, and here we move it like this. These manipulators are quite good to change something, I would say. And now you see, if you follow only these points from Y direction, you see that the wind is running quite fast above the roof, and in the below it's small but going pretty fast in the back when it want to go out of the model here. And if we animate it, you see here maybe with these small balls how quick it is here on top, and now it's coming from the bottom. And what is interesting here, we have a quite high change of velocity after this seating stairway, and I suppose that these people what are sitting on top will have a not so nice haircut afterwards. And with this type of analysis, I coming to the end, and I hope I could give you some ideas what could be done in RFEM with additional programs, and giving back to my colleague Andreas.
Thank you, Andreas, for the nice and detailed presentation. It took more than 1 hour. We are sorry for that. But I hope you liked the webinar as well. I think it was quite important to show the consideration of the stairway because you can see a further benefit of the program RWIND simulation. You can not only do a wind simulation for models with different shape, but also consider objects near the model. Not only such a stairway, you can, for example, consider buildings, bridges, etc. in the neighborhood of the model, and that is very important benefit, I think. How you can create such simplified models showed Andreas in the webinar. You only need to model it in RFEM, this simplified model, and then export to RWIND to consider it. At the end, I want to show my screen the last time. On our website, dlubal.com, you can find free trial versions of the programs, for example, of RFEM with all add-on modules, for example, RF form finding, RF stability, RF-STEEL EC3, all that add-on modules showed Andreas in the webinar. Also here you can find a trial version, 30-day trial version of our wind simulation. Test it with your project. I believe you will like it. As I said at the beginning, in the case of questions about the webinar, about the trial version, you can write us an email, info@dlubal.com, and you will get an answer. Okay, that's all. Thank you for your attention. Thanks, Andreas Niemeyer, for the presentation. Have a nice day. Stay healthy, and bye-bye.